All right, everyone. Beginning section 13.3, last section of chapter 13 that we're going to cover. So we're going to be talking about some of the properties of these vector valued functions and their curves, their graphs. So in particular, we're going to be talking about arc length and something called curvature. All right, so remember the idea of arc length from Calc 2. I think that's the first time we started talking about it. We had a couple different ways to approach it. If we just had a normal function, in this case, I mean function from R to R, that had a graph maybe like this, and we could talk about the arc length, the actual length of this curve between the points A and B. Okay, that had a formula that looked like this. And it's not really worth remembering this form, but when we considered parametric equations in section 10.2, okay, this form became this. We rewrote it in this term. And it's really the same thing. It's just, okay, if we're dealing with parametric equations, we're going to have this form. So remember, parametric equations being something like x equals f of t, y equals g of t, right? Now, what's the difference between this, our usual idea of a function and these parametric equations, parametric curves? Well, we can deal with parametric equations, we can deal with a curve like this. That's not technically a function, right? This doesn't pass the vertical line test, but we can still describe it using parametric curves. And using these parametric equations, we can still find this arc length, which we wouldn't, if we tried to describe this curve as a function of one variable, we couldn't, and so we wouldn't be able to integrate it. But when we consider it from this parametric standpoint, we get this, we can still use the integral. Okay, and now how does that sync up with what we're doing in chapter 13? Remember that these vector valued functions we're talking about, well, those, we could think of them as parametric equations, right? So if I have this vector valued function r of t, and I can think of that, okay, as each component being described by a function. So like the x component is equal to f of t, the y component of my vector is equal to g of t, and the z component is equal to h of t. Okay, so again, we're dealing with a function r from the real numbers to r3. And that's going to be our default for this section, but I don't think there's anything in this section that's unique to R3. We could just as easily do this in Rn, but we're going to stick with R3. Okay. So remember, these vector valued functions might have curves like this, and the curve is in white, and then I've kind of drawn these kind of blue dotted lines to kind of show you what's going on in 3 dimensions. Try to give you a picture. Okay. So we would like to be able to find the arc length of a curve like this as well. Okay. So we want to be able to find the arc length of these vector valued functions, these curves of vector valued functions. And it shouldn't be too much of a surprise that we can just extend our previous idea of arc length, right? There's really not much difference between what we're talking about here with x equals f of t and what we're talking about here. It's just we have one more dimension, right? So really the only thing I do to modify my formula is to add this h prime of t. Okay. So let's just examine this formula and see what's going on. The length, let's say this is my curve. Okay, let's say this is the curve I'm talking about here, the vector valued function. Okay, and let's say, so remember what's happening. I'm plugging in t's to my function r of t. Remember, r of t is taking like a real number, t, which is just a regular number, one dimensional, just taking a number t, plugging it in, and I'm getting a vector out. So maybe at t equals a, I'm here on my curve, and t equals b, I'm at this endpoint here. Okay, so if I wanted to find the arc length from this first point to this last point, okay, I would just integrate this from the t value that corresponds to this first point, right? So if I plug a into my vector valued function, that's going to spit out a three-dimensional point, you know, let's call it FGH. And these coordinates FGH are the location of that initial point there. Okay, so again, to find that that arc length, I integrate what? F prime of t squared plus g prime of t squared plus h prime of t squared, and then I take the square root and I integrate from a to b, where these a and b's, or this a and b, okay, this a is the value of t that corresponds with my starting point here, and b is the value that corresponds with my endpoint there. Okay, now we can get a bit more intuition of what's going on if we try and make a connection with this formula and our vector valued function. Okay, so remember, we're talking about a function, a vector valued function r of t that looks like this. Now think of the derivative of r of t, and then think about the magnitude. And if you compute that, you should see that this stuff inside of our integral, well, that's exactly the magnitude of r prime of t. Okay. And that's not really surprising, right? This stuff inside the integral, that looks like you know, a distance, or a distance formula, or a magnitude. So it's not really surprising. And since we have derivatives in here, okay, that indicates that this is the magnitude of r prime of t. Okay. So we have these things are equal. So we can rewrite our integral formula like this. And this is, you know, much more compact, obviously, and much more convenient to write. So for a vector valued function r of t, if we want to find the arc length from an initial point from t equals a to t equals b, well, that's given by this formula here. I integrate from a to b, the magnitude of r prime of t. So notice I'm talking about r of t, and to find that arc length, I have to differentiate my vector and then find its magnitude. Okay. So let's see an example. Let's say I start with this vector valued function, r of t equals t, 3 cosine t, 3 sine t, between t equals -5 and 5. So I want to find the arc length when of this curve when t is between -5 and 5. So maybe my starting point would be, I plug t equals -5 into my function. That's going to give me some point in R3. That's going to be my starting point. And then t equals +5. That'll give me my endpoint. Okay. So using this formula above, try on your own and find this arc length. Pause, and then I'll talk about it now, assuming you've done it. Okay, and I even left a little room to do it. Okay, so I set up my integral, my initial value as my lower bound of my integral, this upper value as my upper bound of my integral. Okay, and I set up my integral. Well, what's if RT is this, what's R prime of t? And I've kind of spoiled it here, but what I've done is said, okay, if the RT is that, then R prime of t is what? 1, -3 sine t, 3 cosine t, right? Now, and see, I've done this wrong already. All right, so if r prime of t is that, I want to integrate what? The magnitude of r prime. Okay, so what's the magnitude of r prime? Well, magnitude of r prime would be the square root, and then I'm going to square the components. So 1 plus, what, 9 sine squared t plus 9 cosine squared t, okay? All right, so this is my integral, and then I'm integrating in terms of dt. Now, a lot of, in this chapter, in this section, we're going to have to deal with trig identities and some trig integrals usually. So I get what, 1 plus 9, right? 9 sine squared plus 9 cosine squared is just 1, or excuse me, 9. So I get square root of 1 plus 9. So square root of 10 dt. And that equals what? Should be equal to 10 times square root of 10. So that should be my arc length. Okay, moving on. We know how to compute arc length. Now we can create something called the arc length function, which we've seen before in Calc 2 in similar setups from that course. So how can we define this thing called an arc length function? Well, instead of having a bound up in like a real number, an actual number in my upper bound of integration, I'm going to replace that with a variable. Okay. So, and then if that's a variable, well, this whole thing is just a function. I'm gonna plug in different values of t, and I'm gonna get out different arc lengths. Okay. So what this is giving me is this function s of t, and that's going to be the arc length of r of t starting at call it t at well, instead of calling it t equals a, calling it at initial value a up till value t. Okay, so I'm starting with an initial value at a, and I'm going along my curve until I get to the value t, and then this integral is going to spit out that arc length, the arc length between these two values of my parameter. Okay, and since we're talking about parameter, let's talk a bit more about parameters. So this might be a little bit confusing for people because we're talking about this vector in R3, or this vector valued function spitting out values in R3. Okay. So what we have is R of t, okay, where that's just a number. That's just R, okay? So that's a number like 2, 4, 5, and we're plugging it into this vector valued function, and it's giving us points or vectors in R3, right? Now, what is this t? What does this t correspond to? Okay, well, t is the parameter. Okay. And t might be something very concrete, like time. Okay, so we could have a function like this where t is representing time. Then this vector valued function, like at time t equals 0, is giving me this point in R3. At t equals 3, it's giving me that point. At t equals 8, it's giving me this point. Okay, so that's very easy to follow, right? Like at time 0, I'm here, and then as time progresses, I'm moving along my curve like this. Okay. So this parameter t could be something very simple like that. On the other hand, it could be just something totally abstract where, okay, these are just numbers, and yeah, they're giving me different points on my line, but maybe, or my curve, but maybe they don't necessarily correspond to anything useful, any kind of concrete ideas like time. Okay. So we could just as easily use some other parameterization that doesn't have anything to do with any kind of real world concepts. Like we could just say, okay, we have this vector valued function where the parameter is u, and at u equals -5, we're here. At u equals -9, we're there, and at u equals -30, we're there. Okay. So maybe this doesn't make sense from a real world standpoint. Like, what does u mean? Well, u doesn't mean anything. It's just at those values of u, we're at these points. So this parameter could be something concrete like time, or it could be something a bit more abstract. And we can even switch between parameters using something that's pretty much like U substitution. Okay, and we're gonna do this in a moment. Don't get too bogged down in this. We're gonna see how we apply it in just a moment, but in a few moments. But if we wanted to switch between two parameterizations, we call them parameterizations. So if I have this function r of t, okay, where t is my parameter, and I want to switch to some other parameter, I call that a different parameterization. Okay, and maybe t and my other parameter, let's call it u, are related somehow. Okay, so let's say t is equal to p of u. Okay, so these two parameters are related by this function p. Okay, then we can basically just do a u substitution where I say, okay, dt is going to be equal to p prime of u du, right? And then I just I replace t everywhere I see it with p of u, and I replace f prime with p prime of u, f prime pu. Basically, this is the chain rule, right? And so I can easily switch between parameterizations. And a key idea here is that these parameterizations don't affect the arc length, right? When I have some curve in R3, okay, let's say for one parameterization, right? Let's say for R of t, you know, if my parameter is t, then, and let's do this in blue, maybe at t equals -5, I'm at that starting point, and t equals 10, I'm at that endpoint. Okay, that's fine. And then I have this other parameterization. Let's call it R of P of U. So maybe at U equals 7, I'm there, and U equals 43, I'm at that endpoint. Okay, so I got two different parameterizations. But look at the curve itself. Nothing's changed about this curve, right? You know, the curve is unchanged. It's just the values we associate to these points are maybe changing a little bit, but the length of this curve definitely hasn't changed, right? So it shouldn't matter what parameterization we're using. We should always get the same arc length. Excuse me. And that's what we're saying here. Okay, so let's use two different parameterizations. Let's use t, and let's use this pu. And you can try and work this out on your own using that u substitution. You'll see that these things are equal. If not, you can just take my word for it. It's not a huge problem to just kind of assume I'm telling you the truth. So no matter what parameterization, or excuse me, no matter what parameter we're using, whether it's t, u, etc., The arc length, the change in arc length is going to be given by this. Okay. What does that mean? Well, more concretely, no matter what the parameter, it's maybe better to look at this top line here. No matter what the parameter is, no matter what the parameter is, the arc length is going to be the same. So the arc length S is going to be this integral from A to B of r prime of t dt. If we switch to some other parameterization, that might affect these points, right? Just like with a u sub. Think about this as a u sub. If we do a u sub for a definite integral, okay, when we switch to a new variable inside the integral, that might affect the bounds, and it might affect kind of a little bit of how the stuff inside the integral looks, the integrand, but it doesn't affect the numerical answer, right? So that's what we're saying is going on here. Okay. Now, once I have this integral, okay, let's just focus, let's say we've picked this parameterization. And like we've said, it always gives the same answer no matter what parameterization you're using. So let's just, focus on let's say we have this form, okay? Think about fundamental theorem of calculus, differentiating integrals, okay? Try and remember how that works. If I differentiate both sides of this, what do I get? Well, on the left side, I would get ds dt. And what would I get on the right side? Well, I would get r, actually this only works if we have it set up like this. So let's pretend we're talking about the arc length function. Ignore that for a minute. So if we have a t here, okay, that makes this right side a function. If we differentiate that right side, what do we get? R prime of t. We just get r prime of t. And on the left side, what would we have? That ds dt. Okay. So I'm differentiating the arc length with respect to my parameter t. Okay. So I get this. Okay, and that's true no matter what parameter we're using. Okay, if I have what this is saying is essentially if I have this integral, okay, if I'm talking if my if my vector valued function has this parameter, has one parameterization, the arc length, the change in arc length with respect to change in parameter is always just the magnitude of r prime of t. Now, that was just kind of a diatribe a little bit. What do we need to know so far? We need to know how to calculate arc length. Okay. We need to know how to calculate arc length using this formula here between 2 points, or two values of my parameter. I need to know how to set up the arc length function. Okay. Those are the two key pieces of information you need to know. And you need to know that no matter what parameter I'm using, it should always give the same arc length. Okay. Now, let's move on. So we've seen that it doesn't really matter what parameter we use. We could use, I mean, as far as getting a numerical answer for arc length goes, it doesn't matter what parameter we use, we're always going to get the same arc length out. What about for other uses? Okay, so I might want to consider the arc length of this. Maybe I have this vector valued function. The parameter is t. Okay, and I can do all sorts of things with r of t. Right? I could take its derivatives, integrals, and all that, all with respect to this parameter t. But we've seen so far that this t is kind of arbitrary. You know, I could use some other parameterization. And the question is one parameterization better than another? And the idea is that, yeah, you know, all these parameterizations are kind of equivalent in one sense, but it'd be nice if everybody was on the same page, right? Okay, maybe one person's using one parameterization, another person's using another. Is there kind of a default? And it turns out that a really convenient parameterization to use is arc length. Okay, so what does that mean? So if I'm considering a curve here, and I want to talk about points on this curve, maybe I want to talk about, you know, this point on the curve there. If I'm saying, okay, if I have the parameterization R of t, okay, so the points depend on this parameter t. Okay, maybe this is the point that corresponds to t equals -5 or something. If I use a different parameterization, R of p of u or something, maybe this is the point that corresponds to u equals -400,000, something like that. Okay. It'd be nice if there was kind of a baseline for everybody to use. And it turns out that arc length is a really good baseline, okay? So when we have a curve and it's got a nice starting point, okay, where I, you know, maybe I pick it in advance and I say, okay, this is my starting point. Well, it makes sense to talk about this point on the curve, okay? If this is, if, you know, at this point we're s units along the curve from the origin, let's say, let's call it, you know, maybe we're 7, well, maybe this is 5 units away from the starting initial point, let's call it. Maybe this point is 5 units away from this starting point here, meaning we've moved 5 units along this curve to get to here. Well, it turns out that's going to be a very convenient method to use because this arc length, this distance from here to here, that never changes. No matter what parameter I'm using, that never changes. That's always the same, right? So maybe this thing that's kind of constant, it doesn't really change. Maybe that's what we should be using as our parameter. So that's the idea. Now, when we're given a problem like R of t, okay, we don't know what this parameter t is. Maybe it's time, maybe it's arc length. Okay, the fact is we usually don't know. We're usually going to be given R of t equals f of t, g of t, h of t. Does this parameter correspond to arc length or not? Well, usually we're not told. Okay. Maybe we need to, you know, maybe we need to develop a way to figure that out. Okay. So let's assume we're given a function R of t like that. Maybe we're told, you know, some initial point. Okay. And maybe instead of the parameter, we're told, okay, this is the point p equals, you know, what, 1, -2, 3 or something. Okay, maybe we're told that point is on the curve, and that's, you know, we could kind of think of that as an initial point. Okay. Is the function R of t, could we rewrite this somehow? Could we somehow rewrite these components in terms of distance along the curve from that initial point? And even before that, we want to be able to determine, okay, if this is my function, is this in terms of arc length already? So for example, if I plug in 5 to my function, my vector value function, if I plug in 5, Okay, that's going to be what? F of 5, G of 5, H of 5, right? That's going to give me a point on my curve. Okay, is that the point that is in fact 5 units away from my starting value? Or is it going to give me some other value? You know, maybe R of 5 is going to give me some value, you know, way down the line of my curve that is way more than 5 units away from my starting point. Okay, so we need to determine that. So the question is, if we're given this R, this function, this vector valued function in terms of our parameter t, is there a way to tell if that parameter t is our arc length or if it's something else? The answer is yes, we can tell if it's that parameter t is our arc length parameter or not. So let's say I'm given R of t, okay? Now we know that S of t, or let's say my arc length, let's call it S. Okay. This might be a little confusing because I'm switching between t's and u's as the book does. Remember that we can't have a variable in the upper bound of my integral, and we can't use this. We can't use the same. Well, when I have t in the upper bound of my integral, I can't use that t inside my integral as a variable, right? That doesn't work. So if I want to use t as a variable here, I have to use something else like u there. Okay, maybe a better way to say this is, let's say I'm given this function r of u, right? I know no matter what parameterization is that this arc length function is going to be given by this integral. Okay, and differentiating both sides of this, we get this here. Now, what if when I differentiate both sides of this magnitude of r prime of t is equal to 1? Okay, what does that mean? Then that's basically saying what the rate of change, what is the left side? Think about this in terms of rates of change. This is the rate of change of arc length with respect to t. So like change in arc length per change in t. And then what is this? This is change in r per change in t. And it's really the magnitude of the change. Okay. So if that derivative r prime of t is equal to 1, then basically what we're saying is that, well, this change in arc length is 1-to-1 with this change in my vector valued function. Okay. Now, if r of t is at our initial point when t equals 0, then t will be exactly the arc length. Okay. So what do I mean? Let's say I'm given r of t here. That's equal to, and we're working in R2 now. Let's work in R2. We can just easily work in R2. So let's say I have r of t equals sine of t cosine of t. Okay, we're parameterized by t, right? Okay, and let's say we're measuring arc length from this point here. No, that's wrong point. Let's say I'm measuring arc length from here, 1, 0. Okay, so that means, okay, r of t, that's giving me points along my curve. Okay, so maybe at t equals 5, I'm here, etc. Maybe not, maybe I'm at some different point. You get the idea. But we would like to know, okay, is that t the arc length from here to wherever I'm at? Okay. So what do we need to do to test if this, this function is parameterized by arc length? First thing we need to do is find r prime of t. Okay, so I find r prime of t. Okay, so if that's my r of t, what's r prime of t? Cosine of t, negative sine of t. Okay. Now I find the magnitude of r prime of t. Well, that's cosine squared plus sine squared. I take the square root and the square root of that. Well, I know this is 1, so square root of 1 is 1. So I see r prime of t is equal to 1, magnitude of r prime of t. But, okay, to be arc length, for t to be arc length, what do I need? If I'm measuring arc length from here, this point 1, 0, I want to be at that point when t equals 0. Meaning, okay, if arc length is equal to 0, then I should be right on top of my starting point, right? Well, let's plug 0 into this and see what we get. Okay, so when I plug 0 into this, what do I get? I get sine of 0, which is 0, and then cosine of 0, which is 1. So when t equals 0, I'm actually here. Okay. So this parameter t is not arc length because I'm not starting at my initial point. Now, as t changes, let's say t is increasing. As t increases, I'm moving this way, right? Now that change, maybe if I move pi over 4, maybe if t goes to pi over 4, I'd end up right there, okay? Now, let's say r, or no, let's say q is the parameter for arc length. So that, we started there and we moved pi, and then let's say we moved pi over 4, okay, in terms of q. Well, I'd move the same distance, right? It's just the starting point is wrong, okay? So that's because that r prime of t is equal to 1 in this case. So my changes in distance are correct, but maybe I have the wrong starting point. So the short story is, if I'm trying to test to see if something is parameterized in terms of arc length, what I do is I find the magnitude of r prime of t, and then that needs to be 1. And then when I plug 0 in for my parameter, I need to be at my starting point, whatever starting point I'm given. Okay, if both of those things are true, my curve is parameterized in terms of arc length. Okay. Now, the next question that pops up is, okay, what if we're not given, what if we're not parameterized in terms of arc length? Can we convert from some parameter to the arc length parameter? And the answer is yes. And it's based on this same idea that we've seen already. Okay. So let's say I have my vector valued function. It's given in terms of some parameter t. And I set up my arc length function like this, where a is that value corresponding of my parameter that corresponds to my starting point. Then I expect ds dt is equal to this magnitude of r prime of t. Now, let's assume for a second now if t is my arc length, right, my arc length parameter, okay, then I want this to be equal to 1. This should be equal to 1 if t is the arc length parameter. Let's assume it's not equal to 1. Let's assume it's some non-zero constant b not equal to 1. Okay, if that's true, what are we going to have? We're going to have my arc length function, okay, s of t is equal to this integral, and we're saying, okay, this magnitude of r prime, that's just a constant. It's constant b, okay? Well then, if this is a constant, what's that integral? It's just going to be b times t minus a, right? In other words, I have my arc length between a and t is given by, is this right here. Okay, and now let's just solve, let's rewrite, let's get t by itself. Okay, so what do I do? First thing is I divide both sides by b, right? So those cancel, and I get SB equals t minus a. And then I add a to both sides. So I get SB equals t minus a. I add a to both sides, and I end up with this. Okay. Now, what good does that do me? Okay. I have this function r, this vector valued function r of t, where I don't, t is not arc length, right? And then I see, well, t is equal to s, where s is the arc length, divided by b plus a. So I can replace that t with s over b plus a. And now s is the arc length. So now this vector valued function is written in terms of arc length. Okay. So that's how you reparameterize in terms of arc length. So let's see an example real quick. So let's say r of t is equal to this, and now we're working in R3. Okay. So r of t is equal to cosine t, sine of t, t. Okay. And you can check this real quick. What's r prime of t? Okay, if this is my parameterization, what's r prime of t? That's going to be, it's going to end up being square root of 2. Okay, it's not 1, so we know it's definitely not arc length. Okay. T is not arc length. Okay, and that's really the first step. And we're measuring, by the way, we're measuring arc length from this initial point 1, 0, 0. Okay, so what does that mean graphically? Okay, let's see. What was my cosine of t, sine of t, t? Okay. Excuse me. Okay. So my r of t is equal to cosine of t, sine of t, t, and we said our initial point was what? Okay, our arc length is measured from initial point 1, 0, 0. Okay. So what does this mean? Okay. So I have this curve. What does cosine of t, sine of t, t look like? Let's see. At t equals 0, I'm here. As t goes to pi over 2, it's a spiral, and it's spiraling up around the z-axis, right? Like this. Okay, so that's what's going on. And just to reiterate, okay, we want to parameterize in terms of arc length. We've seen r prime of t, and that magnitude is equal to what? Square root of 2. So this, even though we're starting here at t equals 0, okay, if like we're here, if if we're here at time t, or t equals 1, okay, that doesn't mean we're 1 unit away from our starting point. It's going to be off. Okay, so even though our starting point is good, our parameter is not arc length, so we want to convert to arc length. Okay, so the first thing we do is find r prime of t and then the magnitude of r prime of t, and we already said that's square root of 2. And now we can use this conversion trick. Okay, s over b plus a equals t. Now we should note that, okay, this starting point that we were talking about in terms of arc length, that does correspond to t equals 0. Okay, so in my formula, this a is going to be 0. Okay. And maybe to make this a bit more clear, okay, what is this b? That b is magnitude of r prime of t. Okay, and then this a is t value of starting point. Okay, so now we know those pieces of information. We know our r prime of t, that's square root of 2, and we know our t value of our starting point, that's 0. So s over square root of 2 plus 0 should be equal to t. So in other words, I have this. So if I replace t with s over square root of 2, that should give me my my arc length parameter. Okay, and that will in fact be the case. Now let's do the same problem, but let's pick a different starting point. What if the starting point of our where we're measuring arc length from, what if instead of being at 1, 0, 0, what if our starting point was at 0, 1 pi over 2? Okay, going back to our picture. I'm gonna keep the picture. Yeah. So instead of maybe measuring, let's see, instead of measuring from that point there, maybe I'm measuring from this point here, which is uh, 0, 1, 2. Maybe that's where I'm starting measuring my arc length from. So at arc length, at parameter 0, I want to be there. And then if this is s equals 1, that means I'm going to be 1 unit away from that starting point along my curve. So how do we reparameterize my curve, this curve, to get arc length as my parameter with that starting point? Okay. Again, it's just this formula s over r prime of t plus a. So I ask myself, okay, what value a, if I'm using that original function r prime, or excuse me, r of t equals cosine sine t, what value of t gives me this starting point? Well, that would be t equals, or a equals pi over 2. So I plug pi over 2 into this function, I get this point, right? So my a is pi over 2, and we already, the r prime of t hasn't changed from the first version of this problem. R prime of t is, that magnitude is still square root of 2. So I should have s over square root of 2 plus a, which is pi over 2, is equal to t. So in my function, I replace my t with this left side here. Okay, and now I'll be parameterized in terms of arc length for this starting point. Okay. So let's see an example real quick. let's kind of put it all together. Let's say I have this vector valued function, r of t equals sine of 4t plus sine of 4t, cosine of 4t, 3t. Let's determine if this is parameterized by arc length. If it's not, let's convert to arc length measured from the point 0, 1, 0. Okay. So first thing to do is determine if this r of t is parameterized in terms of arc length. Okay, so what do we need to do? First thing we need to do is find r prime of t. Well, what do we want to check? We want to see, does r prime of t equal 1, and does r of 0 give me 0, 1, 0? Okay, I need both of these for my parameter to be arc length. So first step, let's check r prime of t first. Okay, what's r prime of t for this function here? Well, if that's r of t, r prime of t is going to be what? 4 cosine 4t, negative 4 sine 4t, 3. Okay. What's magnitude of r prime of t? It's square root, what? 16 cosine squared 4t plus 16 sine squared 4t plus 9, which is equal to square root of 25, which is equal to 5. Okay, so our magnitude of r prime of t is not equal to 1. So this t is definitely not our arc length parameter. Okay. So we've answered our first question. Next step is, okay, we want to convert to arc length measured from this point 0, 1, 1. So I'm just going to use my formula that I've given you. Okay, I know S is going to be S over R prime of t plus A is going to be equal to t. That's my conversion, right? I want to replace t with this. Okay. So I know my R prime of t. The only thing I'm missing is A. What's my A going to be? Remember, A is the value of t that when I plug it into my function gives me this point, my initial point. So what value of t do I plug in to my function to get this? Well, let's see, I want sine of 4t to be 0, so that could be 0. Does 0 match up with the other two components? Yeah, when I plug t equals 0 into this, I get 1. When I plug t equals 0 into this, I get 0. Okay, so t equals 0 works. So it looks like my A is equal to 0. Okay. So now I have everything I need for my formula. So S over 5 plus 0 equals t. So I should just replace t with S over 5. Okay. So when I do that, my vector valued function becomes r of s equals what? Sine 4 t over 5 cosine 4t over 5 3t over 5. Oh, and those t's should be s's. Okay. So that's arc length. All right. You might take a minute, a few minutes, several minutes, and work some arc length problems. Because curvature, okay, curvature is going to incorporate arc length, but it's, kind of its own beast. Okay, so it's kind of two separate sections, almost. This you can break this 13.3. You can break it up into kind of two pieces. So this would be kind of the start of the second piece. Okay. Curvature. So if we're given a curve in R3, we don't need these, but forget about these dots. Okay, given a curve in R3, one of these graphs of these vector valued functions, we would like some way to evaluate how quickly it's changing direction. Okay, so maybe if I have a curve like this, it's changing direction. If I think about its tangents, okay, what do the tangent lines look like? Okay, these tangent lines maybe look like this. Okay, so it's kind of a gentle slope compared to something like, I could have something like, let's say this is my R3. Maybe I have a curve like this that's like changing really fast, boom. We'd like some way to evaluate that. So this idea is this is going to give us our idea of curvature. Okay, that's where this is headed. Okay, but before we go there, let's kind of build up slowly. When we're talking about these curves, remember we've already seen we can define tangent vectors. Okay. Now, if I have a curve R of t, if I take its derivative, that's not going to be exactly the tangent vector, right? So if I have this function, again, I don't need these points here. So if this is my R of t, I take the derivative, R prime of t, like R prime of t at this point, okay, that's going to give me a vector. What R prime of t gives me is this vector here. Now, this vector is, remember, when we're talking about vectors, it's the same as this vector located at the origin. So really, it's R prime of t gives me what this kind of movement, from maybe it moves 3 units horizontally, 5 units vertically, and well, let's see, we got 3 dimensions, but you get the idea. Okay, so really R prime of t is something, if I had a tangent vector here, R prime of t points in the same direction. Maybe, it's got the same component values. Okay, but if it helps, you can just think of it as tangent vector. Okay. So if I have R of t, R prime of t kind of corresponds to the slope of this 3-dimensional curve. If we're talking about a specific point, if this corresponds to t equals a, okay, R prime of a gives me what? How this curve is changing at that point, that instantaneous moment. But remember that tangent curve, these tangent vectors R prime, they have magnitudes, right? So maybe at this point on the graph at t equals a, my tangent vector looks like this, and maybe at let's say t equals b, maybe my tangent vector is a lot longer. Okay, so these lengths maybe could give some sort of misleading notion about the importance of these vectors, or the weight of these vectors. Okay, and remember we talked previously, that's why we developed this thing called the unit tangent vector. So what we do is we go from R of t, we take its derivative to get R prime of t, and then we just scale this down so its length is equal to 1, and we do that by taking R prime of t and dividing it by its own length. Okay, that's going to scale it down to length 1. And we call that thing the unit tangent vector. It's called the unit tangent vector because its length is 1 unit, a unit. Okay, and we give it the special notation, capital T of the variable t, of little t. Okay. And usually in the book, it's just a bold t, but since you can't really write a bold very well, I'm gonna just do arrows over my vectors. Okay. So this is a unit tangent vector. It's a unit vector that points in the direction of the tangent vector. Now, the magnitude of this thing, t, this capital T, the magnitude is always 1, right? It's a unit vector. Its magnitude is always 1. Okay. So if t changes, right, its length is never changing. So what about t? What about capital T can change? Only its direction can change, right? So this change in capital T, which we could think of as dt, we could think of as kind of a pure expression of change in direction of my curve, right? So kind of going back up to this picture. Okay. Let's say this is my curve R of t. And R prime of t, that could give me tangent vectors, of all different lengths, etc. And then I find t of t, okay, which is R prime of t over magnitude R prime of t. Well, now these are the tangent vectors, but they're all the same length. They're all the same length. Boom. And so now if I kind of put them, if I graph a bunch of them on top of my my curve, they're all the same length. But now when I look at them, I kind of get a clear picture of how my graph is changing, right? This gives me a clear picture of the changes in directions of my graph. And it gives me a clearer picture than if, like, it'd be a lot more confusing if these all had different lengths, right? Like if these were all different lengths, maybe one's like this and one's like that, and then one's like this, that'd be kind of confusing. It wouldn't make as much sense. So that's why we're scaling them to be all the same. Okay. Now I can see that, all right, they're all the same length. So as these, the change in this t, let's call this, it's the unit tangent vector t. So I can see that as t changes, the only thing that's changing about it is the direction. Okay. So that's why I say this change in t, this dt, this capital D, d capital T, that's just change in direction of my curve R. Now, how quickly, this unit tangent vector changes kind of tells me how quickly my curve, my graph of R of t is changing. Okay, so going back up to this picture here. Okay, I have these tangents, these unit tangent vectors, t, capital T, and they're changing. The slope of them is changing as we move along this curve, but they're changing pretty gradually. Now compare that, remember, to our crazy curve, something like this. Okay, if I had something like that, I could again graph my unit tangent curves, but now, like from this one to this one, it changes pretty quickly, right? The direction changes pretty quickly. So that change in the unit tangent vector, okay, is pretty high right here. And maybe it's fairly low for all of these. So we need some way to measure how quickly this thing is changing. Okay, so the question is, what do we measure it against? Okay, now if R prime of t, it depends on what the parameter is, right? If we're using one parameter, maybe this change in the unit tangent vector, maybe it's like, whatever, call it 5. Okay, and maybe if we use some other parameter, its change is, then maybe this will be 47. Okay, so again, we're running into this problem. Excuse me. We're running into this problem of, okay, what parameterization should we use, and is there kind of a standard? Well, maybe you've guessed that we should be using this idea of arc length. Okay, maybe that's the most natural way to measure this unit tangent vector and its change. So we're going to consider this, this quantity dt, d capital T, ds, meaning I'm going to consider how quickly this unit tangent vector changes measured against arc length. Okay, so this dt ds is, you can think of it as how quickly unit tangent changes in response to change in arc length. Okay, and maybe that doesn't make sense. So again, let's kind of go back to this picture. What is that, or a picture? Okay, why does it make sense to, you know, think about it in terms of arc length? Well, think, you know, instead of arc length, just think about position. Okay, so dt ds is like measuring how quickly this t is changing at points along my curve. And, you know, by points along, I mean like, okay, we have some starting point and we're, you know, that many units away from our starting point. So you could also think of this as the change in the unit tangent vector along the curve. Now, there's a special, this is the quantity we're looking for, and we call it curvature. Okay, that this, you know, how big this number is kind of the amount of curvature our graph has. Okay, and we have this notation here. This is the Greek letter kappa, I believe. It's not just a cursive K, it's a kappa. So this we're going to call this quantity dTds, curvature. We're going to abbreviate it by kappa. Now, finding dTds, you know, we want to do it in terms of arc length, but maybe our vector valued function, maybe we're given r of t and t is not arc length. So it would, you know, maybe you're saying to yourself, oh God, well, to find the curvature, does that mean I'm going to have to take my function, convert to arc length, then find this dTds? No, there's a shortcut. So let's say we're given r of t and we want to find the curvature kappa, and we don't want to convert to arc length first. Okay, we don't want to do that every time. It'd be, you know, tedious. By the chain rule, okay, you know, this is what we're looking for, dt ds, right? Okay, by the chain rule, dt ds is the same as d capital T over d little t times dt over ds, which is what? It's the same as this quantity here. Okay, you know, to get from here to here, just think, okay, multiplying by fractions is the same thing as dividing by the reciprocal, right? So we see that this dTds, this kappa, can be written like this. D capital T over d little t, ds over d little t. Okay. What is the top quantity? Let's say I find my unit tangent vector t. Well, that vector depends on what my parameter is, right? For different, if that's my curve, you know, at this value of t, I have one tangent unit vector. At this value of t, I have another vector, another value. So really, this is a vector valued function. Okay, just think of this as a vector valued function, and it's parameterized by t, and I can take its derivative with respect to t. Okay, so I have this vector valued function. I take its derivative with respect to t, which we've done 100 times by now. R prime of t, same thing. Okay. Then what's this bottom? It's the change in arc length per change in parameter. And remember, ds dt from earlier in this video, this is the same thing as magnitude of r prime of t. Okay. So we can simplify this even further. So my curvature at point t, All right, parameter t is going to, this is kind of the theoretical way to say it. It's dt over ds. In practical terms, that's going to be derivative of the unit tangent vector over magnitude of r prime of t. Well, which is equal to this. And notice I'm taking the the absolute value. It's not really absolute value, it's magnitude of a vector, right? I'm taking the magnitude of the top and the bottom. So this is this thing in here. It's a vector. I take its magnitude and I get a number. Same thing on the bottom. It's a vector. I take its magnitude, I get a number. So I get a number over a number, which is a number. So this kappa t is just a number, right? It's a numerical value that kind of describes how much my curve is, turning, how quickly. So this is what you need to know for curvature. Then there's going to be a couple more formulas for curvature. So let's see an example real quick. Let's find the curvature of r of t equals sine of t cosine of t, t. Okay. What do I need for curvature? I need a bunch of things, right? That's my r of t. First I need to find the unit tangent vector t of little t. Okay, well what is that? That's r prime of t divided by magnitude of r prime of t. So really, I guess the first thing I need to do is find r prime of t. So r prime of t, that's cosine of t negative sine of t 1. Okay. All right, so I found that thing. Now I need to find magnitude of that. So I take magnitude of r prime of t. Well, that's what? Square root cosine squared of t plus sine squared of t plus 1, which is equal to square root of 2. Okay. All right, so with those two pieces of information, I can find t. Okay. But what am I looking for? I'm looking for kappa. Remember, kappa is t prime of t over r prime of t. Okay. So I found this denominator already. That's just going to be my r prime of t, which is square root of 2. I need to find t prime of t. So this stuff I can use to find t of t, capital T of t. That's cosine of t negative sine of t 1 over square root of 2. Okay. If you prefer, you can write it like this. So that's your t of t. Next thing to do, you want to find t prime of t. Okay, so you just differentiate this. Okay, you take the derivative inside. Missing a negative there. Take your derivative inside vector. So that's your t prime of t. Finally, okay, what do you want to do? You want magnitude of t prime of t over magnitude r prime of t. We already said in this case, this denominator is square root of 2. So I got my t prime of t. I need to take its magnitude. And you can save yourself some trouble. Let's do this. Forget about this for a second. Let's focus on t prime of t. Well, that's the magnitude of this vector, right? Okay. And that 1 over square root of 2, you could multiply it inside your vector and then compute your magnitude that way. Or you could realize that, okay, this is the same thing as 1 over square root of 2, that absolute value times the magnitude of that vector. Okay, what's the magnitude of this vector? Sine squared t plus cosine squared t. So that's 1. Now I'm multiplying that by that 1 over square root of 2 out front. So my t prime of t its magnitude is 1 over square root of 2. Now I got my t prime of t. I divide by my r prime of t magnitude. Which again we said was, okay, that numerator is 1 over square root of 2. Denominator we already said was what, square root of 2. Is equal to 1/2. So our curvature is 1/2. All right. So it's a little bit of work, obviously. Now there are going to be some shortcuts. You know, this was a bit tedious. There's this formula. So this formula will give you the exact same, well, this formula we just used will always work. This formula here gives the exact same answer, and you can use it in most cases, and it will usually be a bit easier. Okay, so what is the formula? R prime of t cross r double prime of t over r prime of t cubed, and those are all magnitudes. Okay, so let's see how quickly we can do that same example using this formula. Okay, let's say r of t is that same vector valued function. What was it? I don't even remember. Sine t cosine t t. Just a note that this right, so our previous answer was kappa of t equals 1/2. So that means that the curvature of this thing, no matter what t I plug in, is always equal to 1/2. That might not always be the case. It might depend on t. We could have gotten something like 1/2 t squared or something like that. So at different t's, we're going to have different curvatures, right? Which makes sense because I could have a curve, you know, that's nice and smooth and then like gets jagged real quick, right? So here my curve is going to have low curvature, and then, you know, somewhere like here it's going to have high curvature. So that makes sense. But in this case, our curve has the same curvature everywhere. It's just 1/2. All right. So again, let's try and find this curvature again using this new formula and see if it's, you know, any quicker. Okay. So I have my r of t. What do I need? I need r prime of t, r double prime of t, and then this is just r prime of t again. Okay. So I need to find two things. I need to find r prime of t, r double prime of t. So r prime. Okay. Try and make it clear what I'm saying. Okay, this is a vector sign, r prime. All right, cosine, negative sine, 1. Okay. What's r double prime? Well, that's going to be negative sine, negative cosine, 0. All right, I'm leaving out my t's, but yeah, they're there. All right, now what do I need to do? In the top, I need to do r prime cross r double prime. All right. So I got cos, so I'm doing cross products. Let's spread it out a bit more. Cos, negative sine, 1, negative sine, negative cos 0. Okay, this is my r prime cross r double prime. Okay, I do this cross product, and what does it give me? 0 minus 0 plus cosine t I minus, see, 0 plus sine tj plus negative cosine squared minus sine squared. Okay. Okay. So what vector is this? This gives me the vector, what? Cosine of t, negative sine of t, and then negative 1, right? What's the magnitude of this vector? Square root of 2. I can tell just by looking at it. So that's my r prime cross r double prime magnitude. Okay. All right. Next thing, I already know r prime of t, right? So my denominator here is r prime of t cubed. Okay, so r prime of t we said was this. What's the square root of that? Or excuse me, the magnitude of that? Again, that's square root of 2. So what I have is so same formula. And what I would suggest is when you're doing this, when you're setting this problem up, you find r of t, you find r prime of t, you find r double prime of t. And when you're finding r prime of t, I would just go ahead and find r prime of t at this magnitude of r prime of t at this step. Yeah, you can do that before you find the second derivative. So you find these three things, that's your first step. Then you find r prime cross r double prime. All right, so that gives you this vector. Then you find, gives you this vector. Then you find the magnitude, and that gives you square root of 2. Then you divide by that r magnitude of r prime cubed, and you should get the answer. So recapping kappa, curvature. All right. So remember, curvatures we define as this: the change in the unit tangent vector divided by the change in the unit tangent vector per change in arc length. Okay, so that's just kind of the theoretical way to say it, and then the practical formulas are these, where kappa in terms of k, we can either use this formula or this formula. And again, it doesn't matter what our parameter t is. You know, we're starting with, you know, we're doing all this for a vector valued function r of t, and t could be any parameterization. Okay. Now we're trying to find something in terms of arc length, but as long as we use these formulas, it'll all work out the same. We're basically finding our curvature in terms of arc length, but we're walking it through that parameter t, so we never have to actually convert to arc length. Okay. Finally, almost finally, this looks like a lot, but that's actually it. Okay. Normal vectors. Okay. We're going to talk about normal vectors now. First, a little factoid. Okay. So let's say we have a vector valued function r of t. And let's say the magnitude of r of t never changes. Okay, it's constant. So magnitude of r of t equals c. Okay, what would that look like? So something like a circle. We could usually have a vector value. Let's say we're working in R2. So we could even easily have a function, vector valued function R of t, that gives us just a circle. Okay. So what would R magnitude of R of t be? Okay. If my output is a vector, it gives me this kind of, maybe for one value of t, I have this vector here, right? That magnitude we can think of as the radius of this circle, right? And no matter where I am, no matter what value of t I plug in, I always get, the same length of vector. The radius is always the same, okay? Okay. All right. So in that, when we have this scenario where the magnitude of R of t is a constant, okay, R of t, my vector valued function, will always be orthogonal to its derivative. Okay. So what would that look like? Again, going back to that example of the circle. Okay, so let's say we have R of t that's giving us this circle. Okay, well, let's say at a specific point, t, we have, okay, that's our output is this vector. The output of our vector valued function is this vector. And then what would the tangent, r prime of t, what would that vector look like? Well, it'd be this green vector, right? And we can kind of see just naturally, well, yeah, that's going to be a 90-degree angle, right? And it works not just for circles, but anytime that R of t is constant. Okay. So yeah. No, don't believe. Lost my train of thought there for a second. Okay. So let's apply this fact to our. So that's true for R of t when magnitude of R of t is constant. Now, on its own, that's not too useful. Okay, but it's going to become more interesting when we start to think of the unit tangent vector. Okay, this capital T of little t. Well, the magnitude of this thing is always 1, right? When we consider its magnitude, that magnitude is always 1. So this is the scenario we've had just up here. This capital T of t, that's a vector valued function, and its magnitude is always 1. Okay, so then capital T of t should always be orthogonal to its derivative. Okay, meaning, let's say I have, so now let's kind of put it in perspective. Let's say I have some vector valued function R of t. Okay, I'm finding I can find the unit tangent vector of everywhere along this curve, right? And I get this capital T of t. That's my unit tangent vector. That unit tangent vector, okay, I can take its derivative, and its derivative should be at 90 degrees to the tangent vector, okay? So t prime of t. Now, the magnitude of this thing might not be 1. It could be greater than 1 or less than 1, okay? So the length of this thing will always be 1, but maybe when we take its derivative, its length will change, okay? So we have this, but its direction is still 90 degrees to the unit tangent vector. And another way to think about this curve, instead of like thinking about it, okay, it's 90 degrees to this tangent curve, you can think of as like it's pretty much hitting my curve R of t. It's kind of piercing straight through it. It's not hitting at a weird angle. It's kind of like, we can't really say it's orthogonal to this curve because orthogonal is only defined for basically straight lines. So this R of t is not a vector. It's not a straight line. So we can't say this green thing is orthogonal to it. But it's kind of as close as we could get mentally to being at like 90 degrees to my curve. Okay, so this idea is that idea of being, kind of orthogonal to my curve, we would say this vector is normal to my function, to my curve r of t at that point. Okay. So that's the definition of that term, normal. So we say that t prime of t is normal to my curve r of t at that point. And really, we can find t of t prime all along this curve, and it's always going to be normal to my r prime, my r of t. Now, as we said, okay, this length might not necessarily be 1, but just like with the unit tangent vector, it's usually convenient to just always make it 1. So we're going to take this t prime of t and we're going to modify it so it always has length 1. And the results we're going to call the principal unit normal vector, which is a mouthful, so just call it the unit normal. Okay. So when I say the unit normal, I mean this thing, capital N, which is what? It's t prime divided by its own magnitude. So this is going to, remember, this is going to be a unit vector, meaning it's got length 1, and it's going to be normal to the curve r of t. Okay. So let's say this white curve is my r of t. I can find that unit tangent vector, capital T of t, right? It's got length 1. This always has length 1. I find t prime of t, and maybe it's gonna be normal to my curve, but its length might not be 1. Then I divide t prime, okay, so that's t prime, and then I divide t prime of t by its own magnitude, and that gives me this thing n of t, which will also have length 1. And we call that the unit normal. All right, now just a quick wrap up. The rest, that's pretty much all the material, just a couple definitions that you might see in the homework, and a couple one or two quick ideas. Okay, I have these two vectors, right? I can take their cross product. Okay, let's look at what happens when I take their cross product. Okay, if I take the cross product of two vectors, remember I get a third vector that's orthogonal to the both of them. Okay, so I start with these two unit vectors, right? I take the cross product of t cross n. That's going to give me a third vector. Okay, it's going to give me this vector b, and this vector b is going to be orthogonal to t, and it's going to be orthogonal to n. So it's 90 degrees to both of them. Now, this b of t will also have length 1, and we can see that by considering this identity for the cross product, right? The length of b of t, that's what this is. So let's say I want to find the length of b of t. Well, b of t is just the cross product of t and n. Okay, so the length of b is the same as the magnitude of this cross product. And we know from section 12.4, I believe, that this magnitude is equal to magnitude of t times magnitude of n times the angle between them. Well, these are both both unit vectors, so their lengths are 1. And then just from the way we made them, the angle between them, the angle between these two is also 90 degrees, right? So theta is 90 degrees, pi over 2. So sine of pi over 2 is 1. So 1 times 1 times 1 equals to 1. So this b of t, the length of that b of t is 1. Now that b of t we call the binormal vector. Okay, so a little bit of terminology there. I never, and again, this might be something because I'm not really heavy into physics or anything like that, or engineering. Maybe if you're in those classes, you're going to use this binormal vector a lot more. For me, from a pure mathematics standpoint, I never use this, so I don't think it's like you have to learn it for this class, but I don't think it's something you have to know for the rest of your life. Okay. Now, from these vectors, we can also get planes, right? We have some vectors. We can always get some planes from some vectors. So the normal plane. Okay. So let's say I'm at this point on my curve. I can draw this. Let's say I have this vector n, the unit normal vector. I could consider that as the normal vector for a plane, right? So that that vector is perpendicular or orthogonal to a plane that would be butted right up against my curve R of t. We call that plane the normal plane. Okay. And then we can also talk about the, I'm not even sure how to pronounce this because again, it's not something I ever talk about, the osculating plane. So it's not even oscillating, it's osculating. Okay. And that's the plane that's determined by the vectors t and n, meaning this vector b is the normal vector of that plane. Okay, so it's like I have this plane here. That's kind of like, and this osculating plane, it kind of, what it does, it's kind of like the plane that's like most along my curve. So let's say I have a curve, and let's say I'm kind of looking at it from the side, and I have this oscillatory plane that would look like this. It's like basically the plane that captures the most possible amount of this curve. Whereas like another curve like this, well, that curve only intersects at that one point, right? But this oscillatory curve, you could think of as like kind of being most in line with the graph. All right, so that covers all the material. Long video, I know, a lot to process. I would definitely suggest looking at the book for this video. If you've gone through once and you still don't understand, I would suggest reading the book, going to your ebook, reading through the section at least once, and then maybe trying the video again. All right, good luck.